You know, if I asked you what holds the universe together, what would you say? Gravity, the strong force, electromagnetism. Those are all good answers, but they're missing something deeper. Something more fundamental that sits underneath all of it. See, there is this incredible connection that most people never learn about. A connection between the shape of space and time itself and every conservation law we've ever discovered. And when you understand it, when you really see it, the whole universe starts to make sense in a way that is almost too beautiful to believe. This connection was discovered by a mathematician named Emmy Noether back in 1918, and what she proved, what she actually demonstrated with rigorous mathematics, is that every conservation law in physics, every single one, comes from a symmetry in the laws of nature themselves. Now, that might sound abstract, might sound like mathematical philosophy, but it is not. It is the most concrete, most powerful idea in all of physics, and I want to show you exactly what it means and why it matters. Let's start with the simplest example, energy conservation. You've heard of this, right? Energy cannot be created or destroyed, only transformed from one form to another. It is one of the most fundamental principles in all of science. But where does it come from? Why is energy conserved? Most textbooks just state it as a fact, as if it is something we discovered by measuring things very carefully. But that is not the real story. Energy is conserved because the laws of physics don't change with time. That is it. That is the whole reason. If you do an experiment today and get a certain result, and you do the exact same experiment tomorrow, you'll get the same result. The laws themselves don't depend on what time it is. This is called time translation symmetry. The universe looks the same if you shift everything forward or backward in time. And Noether's theorem says, with absolute mathematical certainty, that if the laws don't change when you shift time, then there must be a quantity that is conserved. And that quantity is energy. Think about what this means. Energy conservation isn't just some rule we discovered. It is a consequence of something deeper, something more fundamental. It is a consequence of the symmetry of time itself. The universe doesn't have a preferred moment. There is no special time when the laws are different. And because of that, because time is symmetric, energy must be conserved. Always, everywhere. In every process that ever happens, now, there is a second symmetry that is just as important. Spatial translation symmetry. This is the idea that the laws of physics are the same everywhere in space. If you do an experiment here and you do it over there, 1,000,000 miles away, you get the same result. Space doesn't have a preferred location. There is no special spot in the universe where the laws are different. And what does Noether's theorem tell us about this symmetry? It tells us that momentum must be conserved. Linear momentum, the quantity that measures motion in a straight line, is conserved because space is uniform, because it is the same everywhere. You see the pattern here? Time symmetry gives you energy conservation. Space symmetry gives you momentum conservation. The conservation laws aren't independent facts about nature. They're reflections of deeper symmetries. They're telling us something about the structure of space and time itself. But we're not done. There is a third symmetry, and it is just as beautiful, rotational symmetry. The idea that the laws of physics don't depend on which direction you are facing. If you set up an experiment pointing north and you get a result, then you turn the whole apparatus to point east and run it again. You get the same result. The universe doesn't have a preferred direction. There is no special orientation in space. And what does this symmetry give you? Angular momentum conservation. The fact that spinning things keep spinning, that the total rotation in any closed system stays constant, comes directly from the fact that space has no preferred direction. So now we've got 3 conservation laws, 3 of the most fundamental principles in physics, and all 3 of them come from symmetries. Energy from time, momentum from space, angular momentum from rotation. This is not a coincidence. This is the universe telling us something profound about its own structure. But here is where things get really interesting. There are other symmetries, more subtle symmetries, and they give rise to other conservation laws that you might not have heard about. Take electric charge, for instance. Charge is conserved, right? You can't create a positive charge without creating an equal negative charge somewhere else. The total charge in the universe never changes. But why? What symmetry is responsible for that? The answer is something called global phase symmetry. And this is where we need to think about quantum mechanics. See, In quantum mechanics, particles aren't just particles. They're described by wave functions, mathematical objects that have both a magnitude and a phase. The phase is like an angle, a direction in an abstract space. And it turns out, if you rotate all the phases in the universe by the same amount, if you shift every phase by the same angle, the laws of physics don't change. This is global phase symmetry. And Noether's theorem tells us that this symmetry, this invariance under phase rotation, gives rise to charge conservation. The fact that charge is conserved comes from a symmetry in the quantum mechanical description of particles. Now, that is already pretty wild, but there is more. See? The symmetry I just described is a global symmetry. You rotate all the phases everywhere by the same amount. But what if you could rotate the phase by different amounts at different points in space? What if the symmetry was local instead of global? This is called local phase symmetry, or gauge symmetry. And here's the remarkable thing. When you demand that the laws of physics be invariant under local phase transformations, when you insist that you can rotate the phase independently at every point in space, something incredible happens. You are forced to introduce a new field, a field that connects different points in space and allows the phases to vary smoothly. And that field that emerges purely from demanding local symmetry is the electromagnetic field. The photon, the particle of light, exists because of gauge symmetry. Electromagnetism itself, the entire theory of electricity and magnetism, is a consequence of demanding that physics be invariant under local phase transformations. This is one of the most beautiful ideas in all of physics. The electromagnetic field isn't something we just happen to find in nature. It is required by symmetry. It has to exist in order for the laws to be locally symmetric. And this pattern, this connection between local symmetry and force fields, turns out to be the key to understanding all the fundamental forces. The strong nuclear force, the force that holds quarks together inside protons and neutrons, comes from a similar symmetry, but instead of a simple phase rotation, it is a rotation in something called color space. Quarks come in 3 colors, not real colors, just a label we use. And the laws of physics are symmetric, under rotations in this color space. This is called SU3 symmetry, where SU stands for special unitary. And just like local phase symmetry gives you electromagnetism, local SU3 symmetry gives you the strong force. The gluons, the particles that carry the strong force, exist because of this color symmetry. Quantum chromodynamics, the theory of the strong force, is built on symmetry. The weak nuclear force follows the same pattern. It comes from yet another gauge symmetry, another local symmetry that requires the existence of force, carrying particles. The W and Z bosons, the particles that mediate radioactive decay, exist because of this symmetry. So all the fundamental forces, electromagnetism, the strong force, the weak force, all of them arise from gauge symmetries, from demanding that the laws of physics be invariant under certain local transformations. This is the standard model of particle physics. It is not just a collection of particles and forces. It is a structure built on symmetry. Every particle, every force, every interaction comes from requiring that nature respect certain symmetries. But we're still not done. There are other conservation laws, more approximate ones, that come from symmetries that aren't quite perfect. Take baryon number, for instance. Baryons are particles made of 3 quarks, things like protons and neutrons. And as far as we can tell, the total number of baryons in the universe is conserved. You can transform one baryon into another, you can create baryon, antibaryon pairs, but the net baryon number stays constant. This conservation law is why protons are stable, why they don't just decay into lighter particles. And it comes from an approximate symmetry, a symmetry that holds as far as we can measure, but might be violated at extremely high energies. Lepton number is similar. Leptons are particles like electrons and neutrinos, and the total lepton number appears to be conserved. Again, this comes from a symmetry that might not be perfect, but holds well enough that we can rely on it in all the processes we observe. Now, here is what is so remarkable about all of this. These conservation laws, these principles that govern everything from the motion of planets to the behavior of subatomic particles, they're not independent facts. They're not separate rules that we discovered one by one. They're all reflections of the same underlying idea, the idea that nature respects symmetry. The universe has a structure, a mathematical structure, and that structure constrains what can happen. It dictates the laws. And this is why physics works. This is why we can write down equations that describe the universe. The laws of physics are simple because they're based on symmetry. They're unified because the symmetries are connected. Space and time aren't separate things. They're aspects of space-time. The different forces aren't independent. They're different manifestations of gauge symmetry. Everything fits together because it is all built on the same foundation, you know. When I teach this to students, when I show them Noether's theorem and explain how symmetries give rise to conservation laws, I can see something click. They suddenly realize that physics isn't just a collection of facts to memorize. It is a coherent structure. It is a web of connections where everything relates to everything else. And at the center of that web is symmetry. But here is the thing that really gets me. These symmetries, these mathematical patterns that dictate the laws of physics. They're not arbitrary. They're not something we chose because they're convenient. They're built into the fabric of reality itself. The universe is symmetric. Space is the same everywhere. Time is the same always. Directions don't matter. Phases can rotate. And because of these symmetries, because the universe has this structure, we get conservation laws, we get stable particles, we get forces that make atoms possible, and stars that shine in a cosmos that is comprehensible. Think about what would happen if energy wasn't conserved. If you could create energy out of nothing or make it disappear, the universe would be chaos. There'd be no stability, no predictability, no way to understand anything. But energy is conserved because time is symmetric, and that symmetry is fundamental. It is not something that could be different. It is woven into the structure of reality. Or think about momentum conservation. If momentum wasn't conserved, if things could start moving without anything pushing them, the universe would be incomprehensible. But momentum is conserved because space is uniform, because there is no preferred location. And that symmetry, that uniformity of space, is absolute. The conservation laws aren't just convenient principles. They're necessary consequences of the way the universe is built. They have to be true because the symmetries have to hold. And this is what makes physics so powerful. We're not just describing what happens, we're uncovering the reasons why it has to happen that way. Now, let me tell you about one more thing, something that connects all of this together in a way that is almost too beautiful. In quantum field theory, the modern framework for understanding particles and forces, these symmetries become even more fundamental. Every particle is understood as an excitation of a field, a ripple in something that fills all of space. And the symmetries of these fields determine everything about the particles. Their masses, their charges, how they interact, all of it comes from symmetry. And here is the kicker. When you combine quantum mechanics with special relativity, when you build a theory that respects both the quantum nature of particles and the structure of space-time, you are forced to have fields. You are forced to have antiparticles. You are forced to have the whole structure of quantum field theory. And that structure, that framework, is built entirely on symmetry, on the symmetries of space-time and the gauge symmetries of the fields. So the deepest laws of physics, the laws that describe everything from the smallest particles to the largest structures in the cosmos, are all consequences of symmetry, of patterns in the mathematical structure of reality. And those patterns give rise to conservation laws, to principles that govern every process in the universe. Energy conservation from time symmetry, momentum conservation from spatial symmetry, angular momentum from rotational symmetry, charge conservation from phase symmetry, the strong force from color symmetry, the weak force from another gauge symmetry, baryon and lepton number from approximate symmetries. Every single conservation law we know comes from a symmetry, every single one. And this is what Emmy Noether discovered. This is what her theorem proves, that there is a one-to-one correspondence between symmetries and conservation laws. Every symmetry gives you a conserved quantity. Every conservation law comes from a symmetry. The connection is exact, mathematical, and absolutely fundamental. You know, when I think about this, when I really contemplate what it means, I am struck by how elegant it all is. The universe could have been arbitrary. The The laws could have been a random collection of unrelated rules, but they're not. They're unified by symmetry. They're connected by these deep mathematical patterns that run through everything. And the thing is, we didn't impose these symmetries. We didn't choose them because they're pretty. We discovered them. We found that nature, left to its own devices, respects these patterns. The universe is symmetric, not perfectly, not in every way, but in the ways that matter, in the ways that determine the fundamental laws. And because of that, because nature has this structure, we can understand it. We can write equations that work. We can make predictions that come true. We can build technologies that harness the laws of physics. All of it, all of modern physics, from quantum mechanics to general relativity to the Standard Model, is built on symmetry, on the idea that nature respects certain patterns and that those patterns constrain what is possible. The conservation laws aren't separate principles we discovered. They're reflections of the symmetries, windows into the structure of reality itself. And here is what really amazes me. These same symmetries, these same patterns that give us conservation laws at the level of particles and fields, they also show up in the large-scale structure of the universe, the uniformity of space on cosmic scales, the isotropy of the universe. The fact that everything looks the same in all directions when you zoom out far enough, these are manifestations of the same symmetries. Space is uniform, time is uniform. Directions don't matter, and because of that, we get conservation of energy and momentum and angular momentum on cosmic scales, just like we do in particle physics. The universe is one coherent whole. The laws that govern the smallest particles are the same laws that govern the largest structures, and they're all based on symmetry, on the beautiful, elegant mathematical patterns that Emmy Noether showed us are fundamental. So when you ask what holds the universe together, what makes it work, what allows it to be comprehensible at all, the answer is symmetry. The universe respects certain patterns, certain transformations that leave the laws unchanged, and those symmetries, those invariances, give rise to everything else, to conservation laws, to forces, to particles, to the entire structure of physical law. This is the deepest insight physics has to offer, not that we've measured things carefully and found patterns, but that the patterns come first. The symmetries are fundamental, and everything else, all the richness and complexity of the universe, all the phenomena we observe, are consequences of those symmetries playing out in space and time. It is beautiful, it is elegant, and it is true. The universe is built on symmetry, and because of that, we can understand it. We can see the connections, we can appreciate the structure, and we can marvel at how something so simple, so mathematical, gives rise to everything we see.